All right, everybody, we're gonna go ahead and get started after we fix some audio feedback real quick. All right, perfect. Do this here. All right, we're gonna talk about medium voltage, high resistance grounding today. Let's go ahead and get started. Sorry for all those who are punctual that I made wait 2 minutes, so sorry about that. Let's go ahead and get started. First, let's talk about me for a second. My name is Chris Small. I am a regional sales manager / application engineer for post-level resistors. I've been at the company for a little over 12 years now, and I graduated with an electrical engineering degree from The Ohio State University. Hopefully, the Michigan fans out there can forgive me. Please don't hang up. Yes, all that good stuff. All right, so let's go ahead and get into the overview. We're gonna do like I normally do for resistance grounding topics. I'm gonna talk about resistance grounding for those of you that are new, that need a refresher, all the above. We should go over that first just to make everything nice and easy. Then we'll talk about medium voltage, high resistance ground, what it is, why we use it, etc. Talk about some application notes, then get into capacitive charging current, which some of you may be familiar with. It's very important when it comes to this topic. Some installation, and then a conclusion. Let's go ahead and start with the review. So this is kind of standard across all types of resistance grounding, but usually when you're looking at system failures, whether it be industrial, I've seen reports, or I should say studies in utilities as well. The vast majority of all your faults are going to be phased around. It could be 95, it could be 98, depending on the study you're looking at. The point is the vast majority of them are phase to ground. The other categories are phase to phase, three phase. So phase to phase, we're talking about a phase to ground fault that has degraded, caught a second phase to ground, and then we now have a phase to phase. That's usually how it happens, although it's possible to start off as a phase to phase. And then three phase is very rare. It's usually somebody made a pretty good mistake, typically. So the reason why I bring this up is because, generally speaking, resistance ground benefits you when you have a phase to ground fault. It's very similar to a solid ground system in the other two failure events. So we could talk about incident energy, all this other stuff, but my bottom line is it's essentially the same otherwise, but the phase to ground fault is going to help you a lot. So when we talk about resistance ground, all we're talking about is a resistor between the neutral and the ground, like you see here, in series. So you have the neutral connection XO point here of your transformer, of your generator, going in through the resistor to ground. What this does is essentially, the idea is this will be your only intentional ground path, and you have basically your current on the ground fault being forced through this resistor, it impeding or choking the amount of current that can flow through it. Two typical values would be for a low resistance ground system, like 100 amps, 200 amps, 400 amps, in that range. There's variants, but those are probably the most common. High resistance ground, another topic, what we're going to talk about today, usually going to be 10 amps or below. Sometimes you get a little bit above that, but not normally. So it does, like I mentioned before, limits the ground fault current using Ohm's law. And all you need to remember is that resistance is inversely proportional, whereas the resistance goes up, the current goes down. It does protect equipment and personnel. The lower current you have, the more it does that. Just as an example, for a low resistance ground, you're usually tripping within a fairly quick time frame, and you're trying to limit the amount of damage based on the time exposed and the current exposed as well. It does prevent overvoltages if sized correctly. We're talking about typically intermittent faults in a, for example, an ungrounded system. You might have an overvoltage event based on the system's capacitance. We'll talk about that later. But you should prevent those types of events if you are sized correctly on a resistance ground system. And then for high resistance ground, it can prevent or reduce arc flash. By prevent, I mean on ground fault. Reduce could be, it heavily reduces at low voltage. That's to a lesser extent at medium voltage. Then decreases shock potential from like a straight ground faults or straight ground voltages, excuse me. So let's talk about some design considerations for high resistance ground systems, since we're talking about that today. We're talking about elevated voltages. So when you have a ground fault, no matter what it is, you're going as long as you remain online, you're going to have some imbalance there for voltages. And then for line neutral loads, you're not permitted per the NEC on a resistance ground system to operate with line and neutral loads. So let's go into both of them a little bit more in depth. So we have essentially just a voltage diagram showing you essentially the voltages as it relates to the ground plane. If you have your pre-fault or your normal operating conditions, you're over here on the left-hand side. So this is a medium voltage example. So we have our line to line is 4160. And then we have our line to neutral, which is 2400. And then of course, because your neutral and ground are tied together, you're going to have 0 volts at that point. What happens if you get a fault? Well, now, so this shifts down or shifts away from the ground plane, or actually, whatever, I guess you could say shifts down, shifts up, whichever orientation you want to say. But essentially, the phase-to-phase voltages stay the same, so that's good for your motors, etc. But the two non-faulted phase voltages are going to elevate from a line and neutral orientation right here to a line to line. And so this is definitely a consideration we need to think about when we're designing systems. If you're going to continue to operate with a fault, you're going to have these types of voltages in reference to ground. So it's going to be important to size your equipment, or I should say to make sure your equipment's protected for those voltages. Of course, since you have your A phase grounded, you're going to be 0 there. And then, of course, the neutral is no longer tied to the ground directly, so we're going to have more of a line neutral type value here. So let's move on. Let's talk about line and neutral loads. So this is a picture. Okay.
Yes. No.
Hopefully we're still good on. Had a little technical difficulty there. Okay. So let's move on. So we have a line neutral load here. It's not permitted by NEC. Why is that? Essentially, you could bypass the resistor. We're looking at a short, we're bypassing the resistor. The whole idea of the resistance ground system is to, make sure basically your only intentional ground fault path. You're making sure the current gets choked off, or however you want to call it, impeded, etc. Smaller current flowing through here. If you're bypassing that resistor, you're going to have a greater amount of current. You're also going to have potentially no indication, and so you're going to potentially be in a dangerous situation for your personnel. So that's why the NEC says no. It's a big no on that one. Typically, I don't need to go into this in detail, but usually you would have like isolation transformers if you want to have line neutral loads. That's how you would get by this issue. So let's go ahead and move to the first poll question. See if we can get that up here just to break it up a little bit. Hopefully we'll get that up here in a second. I'll get a drink of water.
I'm sorry, PricewaterhouseCoopers, Anderson Consulting, and Lybrand are tallying the results.
Okay. We have some stragglers out there. That's okay. Hopefully we can close it up here soon.
We can probably go ahead. It's basically split 50-50.
All right. Let's go ahead and move on then. So medium voltage high resistance ground. Typically we're talking about voltages, really it's anywhere above 600 volts. I mean, at least from my perspective, above 600 volts to 15 kV, but most likely you're going to see a 2.4 to 15 kV. Usually does not go higher than 15 amps. We've seen requests for higher than that, but not usually at medium voltage. And honestly, at some point you got to ask yourself, is this really high resistance grounding anymore? But you know, you typically speaking at medium voltage, you're going to have an issue with a lot of energy, more energy than a low voltage resistor system potentially. So you're going to have to worry potentially about how much amperage you have matched to your voltage. Capacitive charging current plays a major role. You're going, you know, there's we'll go into that a little bit more later, but basically it's going to be dependent, the current you have for your resistor is going to be dependent upon the capacitive charging current in part. Historically speaking, you know, I think, and I say this probably even as of 5 years ago, I think a lot of people would nod their head and say yes, you know, for low voltage, use high resistance grounding, or you can, and then for medium voltage, use low resistance grounding, and that is that. And there's obviously some people who didn't do that. They did high resistance grounding at medium voltage. Usually it was for generator protection. It wasn't necessarily continuous operation. But that's kind of historically how it works. I would say more recently, and it's, you know, people can argue how long ago it's been. In my perspective, it's, you know, you saw some 10, 15 years ago, but it's getting a lot more popular now. And honestly, I think there's a little bit of controversy about where high resistance ground is safe. I don't think that controversy exists at 5 kV or below, so that's kind of where I recommend it. What I always tell engineers, I have talked to engineers who have used medium voltage high resistance ground continuously at higher voltages. But I would say if you're not a person who's comfortable with that and understands it, I would say just go with the consensus at 5 kV or below. So, okay, let's move forward here. So it's typically a more expensive solution than low resistance ground. Essentially, you have monitoring equipment. You have a lower current, you're going to usually have a larger enclosure. So the equipment cost is going to be higher, depending on how long you're going to be trying to go without tripping. You're going to have additional wire costs. We'll go over that standard in a second. And any added cost for protection against elevated voltages. So there's added cost in medium voltage high resistance ground. So you might be asking yourself, well, why is it that you just told us that it's getting more popular? Why is it so much more expensive? Essentially, it's all about continuous operation. Do you have an operation that kind of cost benefit analysis, and does it make sense with your being able to continue with the fault? Does it make sense for the extra cost? I won't go into more details about the extra cost, but I'll just tell you that a lot of times the answer is yes. Sometimes it's not, so this may not be for everyone. But usually, whereas low voltage, there's a few different reasons to use high resistance ground. You do have the continuity of service, the continuation on a fault. You have arc flash reduction, severe arc flash reduction. So much so that they say at a line to ground fault there is no arc flash. There is potential there. I would say that gets limited down to just equipment protection and continuous operation for medium voltage, because we don't really see as much arc flash reduction at medium voltage. So, but you have your reason. The processes nowadays are a lot more expensive, and downtime is just a lot more expensive. So I've seen it used both for main power and backup power. I was talking about the increase in demand. I mean, this is just from what I've seen. So obviously I'm not a market guru. However, I think we are a pretty big window into the market. So I would think it's somewhere in this ballpark. We've seen a huge increase in demand for medium voltage high resistor ground in the last 10 years. We do use a transformer to step in, and when I say we, I don't know of anyone, although people are coming out and do stuff all the time. I don't know of anyone who actually doesn't use a transformer medium voltage high resistance ground system. But we do so because we actually tried to do one without a step down transformer. There are some benefits of not using a transformer. You don't have isolation there, so you can do things like capacitive charging current. There's neutral monitoring, etc. That you would have a hard time doing with the transformer. But yeah, so we couldn't do it. It was just too big. It was about a 6 foot wide enclosure. So we decided to go there, just like everyone else, use a transformer. So the market's usually going to use a transformer, and because of that, you're going to have a few less features than a low voltage version on average. So let's go over the NEC requirements for cable at medium voltage. This is an NEC 311.6. Has to do with the cable sizes depending on what grounding operation you're using. So for 100%, you're getting solid ground or low resistance ground, and you're using your standard wires, just kind of a visual aid for people. I'm not the greatest artist, so forgive me, this is not the scale, but so that's going to be low resistance ground, to be solid ground. 133% per the standard, you're going to be using a high resistance ground system that has to clear within the hour. There are people who do this at medium voltage for sure. I've heard, it's a lot more energy at medium voltage. There's a lot more potential for issues depending on what kind of equipment you have. So it's a safe way to go for some people. And then 173% for the continuous rated cable on your ground fault. So just keep in mind that if you are looking to do a medium voltage high resistance ground system operating continuously or operating, more than tripping quickly, you might have additional cable costs there, or you will, depending on how long you do. Just from my experience, I've seen a lot on pump stations, oil and gas, 5 kV application. I've seen a lot on data centers, usually on generators. For data centers, it's both for generator protection, but also for even continuity of service at 5 kV. And once again, that any 5 kV or below application where continuous operation is important. So I guess the main message is it's doable. The question is, besides what we've already gone over, there are some design considerations. So HRG for generator protection, I say this is more common above 5 kV. Really, honestly, probably overall, it's more common than the continuous operation of HRG. But the idea is that you want to protect your generators from stator faults, essentially. We'll talk about that in a second, but sorry about that. Okay, so you're either tripping offline after the wind down occurs or continuous operation. So those are your options. There is some controversy. I'll say it again just to make sure that nobody gets mad at me. There is some controversy, and some people may tell you there is no controversy. You shouldn't do it. I'm just saying I've heard both sides of it, and I don't want to really take a stance on it, to be honest with you. So I personally would not do it. I don't feel comfortable with it, but I also have never really designed a system by myself before, so there's that. So let's go to more why. IEEE, the Green Book, essentially, so your generator has reactances, both zero sequence and positive, and there could be a disparity between the two at startup. So you could potentially have currents that are greater than the ground fault currents that are greater than your bracing. And if you have that situation, it's really bad news. So I truly recommend that you use some kind of impedance ground, which I argued in the past. Most of the time, that means resistance grounding. You can get that kind of takes care of takes care of that situation with the generator. So you have elevated currents that can happen. So you typically need an LRG, but you can also use an HRG. That's as long as your charge current's low enough, that would fit that requirement. And that HRG gives you the added benefit of having, the case of stator faults. So if you have a stator fault, essentially, we'll touch your finger there. You have a stator fault. Essentially, you could potentially have a situation where, I think I've gone over this in our hybrid grounding webinar before. But essentially, you trip here, but your generator is still winding down, so you have some additional damage that can occur here. If you had a high resistance ground system tied to the generator, you would not have to worry about this additional damage on the generator. So that's kind of the idea of it. And so once again, if you talk about hybrid grounding, that's kind of the situation where you can't use high resistance ground exclusively because of the capacitive charging current, but sometimes you can because of the charge current is lower. So I know I've said a lot about the charge current. We'll go over more detail in a second. So if you just have a low resistance ground system, just as an FYI, it's possible that you can get additional damage. It has been shown in some IEEE papers for some pulp and paper facilities out west. So in terms of the HRGs, I mentioned about the charge current, and you can get complete protection no matter what kind of fault you have, either stator or system fault. So there is some benefits to it. It is fairly common at 5 kV, 15 kV. I see a lot of 15 kV, a lot of data centers at 15 kV. I can mention, I don't know, a lot. And we've done millions of dollars with this type of application for generator protection. Ideal for larger generators or generators in parallel. Where hybrid grounding, where you can get away with not using hybrid grounding because of the capacitive charging current. So let's go to poll question number 2, just to take a break, and we're gonna go through the third part of our presentation.
The accountants are once again hard at work.
Just as you guys do that, I just want to remind you guys, I may have forgotten to at the beginning, but a couple things. Number one, if you have a question, go ahead and put it in the question box. We'll try to address it now or at the end. We'll kind of do a little Q&A at the end as well. If you have comments like, it's summertime, Chris, why are we doing this at 3:30 in the afternoon? I want to be at the pool or something like that. You can leave that as well. We've had it at 3:30 for a long time, but I'm just curious. But if just as an example, but if you have any comments at all, no problem. We'll definitely take those as well. We may not bring them up in Q&A, but.
All right, we're going to consider it closed. This time, 60% of people voted no.
All right.
They have not gone through that wonderful experience as of yet.
So there's a little bit, yeah. I think that part of it is a lack of familiarity. Part of it is, it's not worth it for the cost. I think it's getting a lot more popular, but it's not going to be for everybody. I think I can, in my mind, I think I can say to myself with a clear conscience at low voltage that I can't imagine an industrial application that's really going to be worse off with high resistance ground, maybe a handful, but the vast majority. With medium voltage, it's a little bit more nuanced. I mean, it's not a slam dunk. You need to do a little more analysis and a little cost benefit analysis and figure out what you want to do. But it's still very good, and I think that's one of the reasons why we're talking about it. So I mentioned it 3 or 4 times. Let's talk about capacitive charging currents. You know what? Let's see. Yeah. So let's talk about capacitive charging current. Capacitor is 2 conductors with an insulator in between. You basically have that in any type of scenario in your system. You have it for parallel cables, you have for motor windings, all kinds of different things. Really, you have a small level of capacitance all throughout your system, and that total adds up to your system's capacitance. And your system's capacitance, in terms of line to ground, can compete with your ground fault current in terms of current. And so you can actually carry current on the capacitive charging current. That's why it's called that. So you have it here. This designates your capacitive charging current. You essentially have a faulted phase. You're going to go essentially have a vector sum of your currents here, and that's your system's capacitive current. So if you had, like I mentioned this before, if you had an unground circuit and you had intermittent fault, you could potentially charge this here and get over voltages. So when we have a resistor, we need to make sure that the current level for the ground fault is higher than this level. That's the idea. So we really can do, in terms of calculation, in terms of how you figure out what your capacitive charging current is. I do not believe, although I may not have 100% up-to-date information, but I don't believe any modeling software does this yet, or is planning on doing it. I could be wrong. If that's not true, let me know, because I don't usually deal with modeling software that often, but I have not heard any feedback that it does. So essentially, you can do 2 different ways. There's a lot of nuance, and then part of it is you can do calculation. Here's kind of your basic formula here. Your 2 times square root of 3 pi volt line voltage, frequency, and 0 sequence capacitance. You may, on some of your equipment, you may, like wire, for example, is fairly simple. We'll talk about that in a second. But for some of your equipment here, you may need to work with manufacturers to get the capacitance info. It may not be that easy to figure out. So the calculation may or may not be possible or easy. But I would say with wire, it's almost always easy. I mean, as long as you know the size of your wire, essentially you have your a derivation of the formula here with wire, and so you have your same charging current. This is your line-to-line voltage. Inside C is the specific inductive capacity of the insulation. Do you have to know exactly what that means? No, I'm not sure if I can explain to you. All you really need to know is, look, depending on what you're using, you can use a certain factor to put in that space. Then you have your diameter of your overall cable, and then the diameter of your conductor. So you can calculate this fairly simply, and usually the wire is about 80% of the capacitive charging current calculation. So you're going to have the vast majority of that system done. So when I'm looking to do and this is just me personally, you guys may have your own preference. I try to use a combination of the two because I don't have, I've worked with customers who try to completely calculate all of their equipment, and the vendors, not all vendors, some of the vendors are like, oh yeah, we'll look into that, and all of a sudden it's 3 weeks down the line. And I don't know if they sometimes don't know the information. It's hard for them to get to. So just one of the ways you get by that is for the stuff besides the wiring, you can use established tables, kind of estimations based on what you have. A certain amount of kW motor, generators, different types of things, surge suppressors, etc. And there's kind of actually published tables based on what you have. And you can kind of see here that there's much lower values for low voltage, which is typically the vast majority of the time at low voltage, you don't have to worry about this. You know, it's still an issue. We have the ability to measure in our system that makes it a little bit easier. But the point is that 95 plus, or probably 98+% of the time, with some notable exceptions, probably data centers is one notable exception, you're going to have lower capacitive charging current. But then, as you can see, as you get up higher, you're getting up higher and higher. You have larger conductors. You're going to have typically higher values at medium voltage. So you're going to be able to have smaller systems and still have charge currents too high to meet the threshold of a high resistance ground. So just again, I didn't mention before, high resistance ground, you really want to have the ground fault current higher than the capacitive charge current. So here's just an example of some of the components. You kind of just tabulate up all the stuff you have in your system. Take your one line, take all the stuff, take all X amount of feet of cable of three odd, or you know, whatever you have, 8 gauge or all that stuff. Just tabulate it all out, put it in a spreadsheet, figure out what it is per 1,000 feet, or measure your wiring first, and then use these tables for your other gear, or calculate it. I mean, it's all up to you guys, but I'm just trying to give you a window to how to start the idea of how to do it. I personally try to mix them both just to kind of make it a quicker analysis and still keep it fairly accurate. Usually you're going to be more conservative. If you have the estimation, you're going to land on the conservative side. So at least you're not going to be undervaluing it. Another thing to speak, a lot of times we get in the situation where we have parallel generators and we're looking to try to figure out, well, how do I do my capacitive charging current? How can I figure this out? Just so you know, essentially ground fault current is additive when you parallel. So we're talking about overall systems of 8 amps. So in this scenario specifically, you have 8 amps of HRG ground fault current, and then your system's capacitance would have to, or charge current would have to be less than 8 amps, right? But that's not usually a realistic example because you don't parallel generators so that you will always run all 4 at the same time. So it just kind of simple math, right? You can go 3 generators, and you'd have, you know, if that's the worst case scenario, then you have to be under 6 amps. If you were just 2, you have to be under 4 amps. You get the idea. Then 1 would be the 2 amps. So you need to make sure this is kind of a consideration you need to figure out. We've had, you know, at low voltage, we had a customer that wants to do 25 amps because they have 1 generator at their system, and that's a little bit high. I don't like it to be that high, but you get the math is simple. You get the idea. It's something to consider. You definitely want to consider that. In terms of installation, typical locations, you get a concrete pad next to the source. If you have a seismic unit, it needs to be anchored to the ground. We do have some seismic units. They're not this. These are our full continuously monitored HRG systems for continuous operation. These are actually 36 by 36. You see this footprint indoor right here. You know, I did mention before, I don't know for sure why it's getting more popular. One reason may be because, you know, I think UL is becoming, you know, we've had UL for a while. I don't know if anybody, there may be some other vendors who have UL, but maybe the introduction of UL made it become a lot more popular. People understood that, okay, well, now it's acceptable. They just were more comfortable with the idea if it's UL label, we can maybe do it. So that's another issue that may have driven that popularity. But typical locations, you have a concrete pad. You can put it in an e-house. We have a lot of people put it in e-houses. You know, you just basically have these eye hooks you lift up into an e-house. But our footprints, these are 36 by 36 is pretty small for me, voltage high resistance ground. I know of at least 1 analog unit that is this big, but I don't know of any other digital units that are like that. But then our outdoor is 42 by 42. I just give you some examples of a footprint for what you would be looking at. I'm not trying to. I just know those examples, so I'm just not trying to sell you just on post lever. So, but you could be a wall-mounted transformer. It is possible. We have made them before, although they don't look a little bit different than a low voltage unit. Continuing on, we have a freestanding unit. So in terms of working clearance, You always, for any piece of equipment, you're gonna need working clearance on at least one side. So you would need that 4-foot working clearance. Typically it would be in the front for the unit I just showed you. For a unit more like this, you probably would just pick the side, which is more easily accessible. You need to have 1 foot on the side. That's not electrical clearance. That's actually, for our units, you have a certain, typically 385 degrees C for continuous operation. You need to make sure there's some separation there, some airflow that can be gotten. So that's why there's that. In terms of connections, they're usually pretty simple. They're a little bit less simple, a little bit more simple than our low voltage design, just by the 3-phase connections. But you don't have that. You have the EXO connection, neutral connection, then you have the ground connection. So it's a pretty simple installation in terms of the wiring. Then if you had communications or stuff like that, you add that as well. So honestly, that brings us to the conclusions. We could have gone a little more in depth, but there's a lot of stuff to go through. I wanted to keep it around 45 minutes. So medium voltage high resistance ground used continuously is safe with proper considerations. Those being, capacitive charge and current. You need to make sure. I would say that if you're going to do medium voltage high resistance ground, and you don't absolutely know for sure that capacitive charge current is low enough, you have to do an analysis. I think it's prudent. I wouldn't say the same thing for low voltage, but I would definitely say at medium voltage. Design considerations are followed, like talk about the over voltages, talk about the line of neutral loads. Medium voltage high resistance ground is an effective way to achieve redundancy, continuous operation with the ground fault. I talked about the additional costs. I think you guys understand how much benefit it is a lot of times for process. I did another presentation on the economics of resistance grounding, so there's a lot of lost money and downtime. So it's very potential that your client would be interested in something like this, or you would be as well. And once again, I wanted to stress that the consensus for safety is for 5 kV and below. At that point, your voltage is low enough. For example, if you have 13.8 resistor, you have 10 amps ground fault current. That's a lot of wattage. There's potential for arcing potentially. So it's once again, if you don't have a comfortability with it, I would stick with that consensus. So we talked about it before. Hopefully there's some questions. If there's something I didn't go over, or if there's something that's not clear, please ask away. If we don't get to your question, don't feel slighted. We'll definitely get to it, depending on how many questions we have, depending on the relevance, etc. But we'll definitely answer your question regardless via email if we don't get to it right now.
A question from earlier in the presentation, and you kind of touched on it, but I think it's a good summary type question. Is it correct to assume that for medium voltage HRG system, we use it to reduce the fault current and then trip, but not necessarily for continuous operation?
It depends on what your goals are, and once again, no. So when I keep saying it's a consensus for 5 kV and below, that means for continuous operation. So doesn't mean you can do it. You need to make sure that you can operate. There's a lot of people that prefer to operate their medium voltage high resistance grounds with a stipulation of tripping after 1 hour. There's other people that do it continuously. You can do it. If we're talking about generator protection, the vast majority of the time, we're talking about 15 kV and lower. Usually you trip on those. To be honest, it's very rare to not, but I'm not saying it hasn't happened. I've seen it before. But yes, I would say it's once again, that's why I was talking about the controversies. There's not really any controversy to continuous operation under 5 kV, assuming that the design considerations are met.
What amperage is the resistor typically for a 5 kV HRG system?
It is exclusively, let me think about this. I can't think of anything else. I would say it's exclusively dependent upon the capacitive charging current. So it's really case by case. I would say on average, if we're talking about just normal stuff, usually it's a little bit higher. We're talking, in the 8 to 12 amp range. We do have some customers that do 12 amps. We have a lot more that do 10, just because their capacitive charge currents are a little bit higher than normal, and they need to get a little bit higher. So yeah, I would say 8 to 10. I think one of our units is 7 to 10, and then we do a 12 amp unit. So yeah, but it's usually a little bit higher. Then again, if you're just talking about generator protection, you could be talking about a very small amount. If you don't have very much at all, and you're just looking to protect the generator, you're literally just looking at a little bit of cable and the generator in terms of capacitive charging current, and you may be able to go very, very low. So.
Let's see, is medium voltage HRG design affected by power factor capacitors on medium voltage buses or motor applications?
The answer is yes, but you could. I know that you can. Well, for medium voltage, I assume I can't think of an example, but I'm sure that there are delta oriented phase correction capacitors. So whenever you have a piece of equipment that has literally a capacitor on it, you're going to be drastically impacting the capacitive charging current. For some things, there are ways around it, and one of those ways is to actually hook it up delta. Now, you can't do that with everything, but I think that's a good example of something you could do. The phase correction capacitors, they usually can be hooked up and not line of ground.
Is there an option for environments that require NEMA 12 enclosures?
Well, I don't. For our particular offering, when we have our standard offerings are NEMA 1, NEMA 3R. We could do the medium voltage. We could do a NEMA 4X control panel with a resistor. But we typically have different offerings depending upon your situation. Now, if you come up with something special, will it be UL? It's hard to say, but most of the time we can come up with a solution that meets your needs.
I think if I can throw on to the end of it, obviously with a resistor and a transformer, there's a tremendous amount of heat generated. If you're willing to place them somewhere else, you can do a high degree of weatherproof, dustproof for your control cabinet. But due to the heat the resistors generate, they do have to be isolated and ventilated significantly.
Yeah, I appreciate it. So yeah, that's one thing that I didn't mention. Yeah, these medium voltage HRGs do give off a lot of heat. There's a lot more heat than low voltage. So that's definitely could potentially be an issue. That being said, it's possible we could do something about it, but it probably would not be UL.
I'm going to do one last question. Can you give rough costs? We talked throughout this about, it's a higher cost than a low voltage unit. So for example, 5 kV systems, if I needed a Y medium voltage high resistance grounding, what am I looking at typically cost wise in ballpark terms?
I can give you a guesstimate. I do know that 130, we're talking about like 133% cable. I don't know if you guys heard, if you buy like 5 kV cable, you can buy like 5 kV 133, you can buy 5 kV 173. You can also go up a grade, you can go up to 8 kV. That's an option. So you're basically, honestly, at this point, I don't even want to give you a number because I looked at it for a while, so I don't know the difference prices of wire. Just
the resistor cabinet with controls. I apologize.
No. So medium voltage is typically for a Y is typically in the $20,000 range, depending if you kind of go with the standard Y without like stainless steel or just kind of normal. That's kind of where you're looking at in the $20,000 roughly. Delta would be probably add 15-ish, maybe even 20-ish to that. And then if you go stainless steel, you're going to be adding on the top of that. So there's just different things, but your normal, normal one would be 20/low 20s for the, if you want to budget it, I would say start at 25, just add $5,000 number I just gave you for a budget cost, but
I think I know we're starting to run up probably on time for a lot of people. Chris, thank you. I'll let you wrap up quickly before we do. There are a couple of questions that have gone unanswered. They're obviously very interesting. There's some about UPSs that probably would run long in this forum. We'll definitely reach out and try and get you the answers you need. And I'd of course like to thank all of our listeners today from Canada. Thank you for participating. Chris?
okay. Well, thank you guys. I appreciate it. If you have any questions, this is I tried, it's almost an introductory to the topic. I did, there has been papers that have been done that, that are probably more of a longer term. I just want to kind of give you an introductory idea of this. If you have questions, please get back to me. Get back to us. We'll definitely answer them. But I just, hopefully this was at least an introductory level topic for you guys. So hopefully you guys enjoy your summer. We'll be back next month with dynamic braking versus regenerative drives, kind of a cost analysis / when should you use it, when should you not, what person kind of pit those two against each other. So hopefully we'll see you back next month, and take care until then.